Hey everybody, the green screen is going haywire right now. You might be watching. I'm gonna go over here and see who's live with us. I'm trying to fix it as we speak, and so I was doing that for the last 5 minutes because I think it's the blue shirt. I wore the crash shirt for the first time today, and it's Wacky Wednesdays, so I don't wanna broadcast like this. Who we have in the chat? Here we go, Jennifer and Cameron. Good to see you. We're gonna try to fix this real quick right here. But it's like, good morning, how you feeling? I'm a little bit better. I've been coughing at night, which is the bummer part. That's the not fun part of like being sick. Like other than that, I'm doing pretty good. Like I don't have a fever, all that good stuff. So you're gonna see the behind the scenes. I'm gonna go over to um, the the camera green screen. It keeps on registering this top part as like it keeps on doing it, but I've got the alpha too high, so it's not registering my hair right now. So look at that, look at that. What in the world? Also, look at it creeping down. It's like, oh, gonna not green screen the green screen. What are you doing? Should I just grab another light real quick and light the green screen more? Like, trying to think how I could do that. Okay, let's see. He keeps. Oh, and then I'm the alpha. It's man. It looks like it's good. I need to put a white background behind me. 2 seconds. Sorry, we're doing this. Sorry. What should we do afterwards? What should we do? Put some comments in the chat of what we should do as Brian tries to make his head not disappear. So put some comments on what we're gonna do, and we'll do that here next. Of course, it's a wacky Wednesday. So, chapter 19. I want to ask Terry if he has a key light. Seriously, like 2 seconds. I'm gonna see if Terry has a key light. Green screen craziness, Terry. We got a light. Got a light. Yeah, it like literally the way it is. I can't like yeah. So it's and then it will start creeping down, and it's
like you're in the Matrix.
I've been trying to reformulate it. So okay, thank you so much, Terry.
Oh, you're welcome. And if you need other ones, just have them.
No. I'm not gonna steal two things from you.
Alrighty.
Thank you, Terry. Yeah, you can close it. Appreciate that. That is teamwork right there. Makes the dream work. No. Do I need an extension? Oh, wait, I got an extension cord. Do I have an extension cord? My gosh. What luck for me to have an extension cord in here. Okay. We're almost there, everybody. Comedy of errors this morning. Got to plug into the thing with everything. And we'll do some, oh gosh, hit my head. Don't worry, I'm all right. I want that, oh, because it's the other way. Okay, we are plugged in. I just booped my head a tiny bit. Okay, we're plugged in. Now we are going to plug in this right here. Now we're plugged in with this. Now we got a key light, which we haven't had all year. Now we have illuminated me. Good morning. I think people can still hear me. So now I'm more illuminated, which is the key to green screening, is illuminate your subject. Now, since I am illuminated more, supposed to be, we'll be started here in just 1 minute. I started up today and the lighting was just like, nope. So, sorry everybody for the delay. There we go. I am more illuminated. And let me try to fix this now. It should be better fixable. Finally, oh my gosh. It looks even better than before. My gosh, sorry everybody. Okay, let's do some chapter 19. What question should we do? Chapter 19. Let's do it. We finally got it. And I think the video even looks better than it's been all semester. Yeah, no, you have to find the right green screen color. You have to put the right settings on everything. And we're still getting a little artifacting. We'll deal with it. Looks good. I'm fine with it. We're not going to spend all day working on fixing this. So I had it set, and it just probably is the blue shirt. I didn't realize it. I hadn't worn the blue shirt all semester. You don't wear green with a green screen. Don't do that. But I could work on the camera and fix things. But huge thank you to Terry right there. I just kind of ran over to his office. I was like, I need a light. And he's like, okay. So, Jai me butt. Oh man. Yeah, I am getting some artifacting. Whatever. But thank you everyone for going through that. 10 minutes utilized on that right there. 10 minutes. 10 minutes. He not. Assignment Manager, chapter 17, or 19, we're doing 19. Finally, my person's back up. So, place questions. We could probably do all of chapter 19 quiz. You want to just do all of chapter 19 quiz? Knock it out? Complete chapter 19 quiz. Not a bad quiz. Let's do it. Okay, finally getting started here at 11:53. Chapter 19, a certain story. Oh man, here we go with the first one. Let's do it. Don't you dare green screen start acting up on me. Certain war story right here talks about injuries people get during a war. Everything reformulated. We've got all the injuries during the war that people get, and this is an interesting thing about this question. When we do the null hypothesis, in chapter 19, there's an easy way to remember it. Are you ready? The easy way to remember it is x is independent of y, and the alternative is x is not independent of y. You look at the two variables, injury site and lethality, and what is the null? I want you to say it in the chat, then we're going to go find it. Don't look at their answers. Remember, if we can figure it out without looking at answers, we've learned it. So the null is x is independent of y. So you input the names of the variables here. This is the chi-square test of independence when you have two categorical variables. That's when we use the chi-square test of independence. So what would the null hypothesis be where we say x is independent of y? How would that be? We have two categorical variables. The chi-square test of independence is x is independent of y. So what would the null hypothesis be? I think it does look way better. Like, gotta fix other things. I need someone to write the null in the chat. Remember, don't look at their answers. Don't look at them. You've just got injury site and lethality. So that's x, that's y. So x is independent of y is the null. We just input the names of the x and y variables. So what's the name of the x variable? What's the name of the y variable? And so just think and try putting in the chat, x is independent of y. This is practice for the test because you remember the chi-square test of independence. We have two categorical variables. The null hypothesis is x is independent of y. We just literally input the names. Just we have the x variable, injury site, that's the name of it. So input that for x. Lethality is y. So has anyone got it? Lethality is independent of injury site. Exactly. Great job, William, right there. And the alternative is lethality is not independent of injury site. You can say dependent. That works too. Good to see you, Colin. So with this, site and whether or not people are die from it are independent, and the alternative is they're not independent. I like to say x is independent of y, x is not independent of y. And there's other ways to phrase it, like x has a relationship with y, like that's what not independent means. So be careful, they will try to trick you with some alternative wording. Know the alternative wording because there are other ways to phrase things. Now we get to the expected values. Now this is where we should know the formulas. But jump's going to make our life easy. Go here to the table and go to the button here and copy to clipboard and then make sure to hit Command or Control C. Now go into jump. I'm going to blank my screen for a second. When you go into jump, you want to go here to File, New, Data Table. And then make sure this time to go to Edit, Paste with Column Names. Paste with column names. Now you're going to get counts for each group, and you're going to get the injury site and the fatal and the not fatal. And I was going to say fatality of it, fatality. But now go here and go to Tables, Stack. We're on Tables, Stack. With Table, Stack, double-click the quantitative columns. Double-click the quantitative columns. And you should see this result right here, where you have two categorical variables, and then you have the count over here on the right side. So you have your categorical, and count. Go ahead and click OK. Now that you've done this, this is the final thing we want to work with. Increase the font a little more so you can see. But you should have a column that is categorical, another column that is categorical, and the data column. You can double click right here and call this site. It doesn't matter if you do that. You can call this outcome. But these are just need to be categorical, categorical, and with the counts. You could also enter these in manually, but we're going to analyze this with analyze fit y by x. Under analyze fit y by x, we're going to put does site explain why there is an outcome, and then we need to put the data here in frequency. The most common issue people have is they don't put the data into the frequency. If you don't put the data into the frequency, you will get a mosaic plot that's completely flat across, and that means you didn't put in the counts. So make sure to put in the count or the frequency of observations right there. Now when we run this, we get a mosaic plot. And as you would think, where you're injured is going to lead to more or less lethality of the injury. So you can see right here, the most lethal spot to get hit is in the head or the neck, next body, and limb. Most people were hit in the body by the marginal display right here. Remember, a mosaic plot shows you the percent of the observations in each group. If you look across the margin and trace this way, you can see the percent for body, the percent for head, and the percent for limb, if you think of this out of 100% going across the bottom. The other, I know, oh, I like mosaic plots. And then the other marginal display is the percent there are in each group for not fatal and fatal. They can also be seen in the table right here with 17.11% fatal. That's that blue bar right there. And also the percent limb can be seen right here in this marginal, 22.37. So remember, the contingency table shows you the percentages, and you can find out the percent of limb injuries, the percent of head neck injuries, the percent of body injuries, which is 46% going across the bottom. The inside of the mosaic plot is the bivariate relationship. So with this right here, we need to get the expected counts. Now, what are expected counts? Expected counts are what we would expect if there is no relationship. Just think about this. Since we know right here, let me put the counts back on here too. So we know that 71 of the injury sites were body. We know that about 11% are fatal. So if you think about this, and this is kind of the math we'll be doing, I don't know why I never saved a calculator. I'm going to pin it. I pinned it. I unpinned it. 71 times about by, whoops. 71 times by about 11, or nope, 0.11, is going to be about that expected count. I didn't get the right amounts. It was like 18% or something. Let's show how to do this. And this is where you need to practice for the test. So for practicing for the test, let's take a screenshot right here. I'll show you the screenshot in a second. This is going to be how to find expected counts. Okay, how do we get expected counts? Know this formula. Row totals times column total divided by grand total. So this is the formula right here for all the expecteds, row total times column total over grand total. And it's pretty easy to do. So for this cell right here, what is the formula to get 58? Just write the formula as though you're solving it. And I'll show you what you want to do. Row total, column total, grand total. And you can basically just write it out. So go ahead and show me in the chat you're following along. And you know how to write this formula that will get you 58.85 when you're figuring out the expected cell count. Like, how many people would we expect to have fatal injuries in the body? Given this data, how many people would we expect? And it'd be 71 times 126 over 152 exactly. If you think about what you're doing right here, it's very interesting because you're actually doing the multiplication rule. You're doing 71 times 152 times 126 over 152, and then to turn it out of a decimal, you're timesing it by 152, which cancels both of these. Now, what assumption do you have to make to multiply two things? What assumption did you have to make to multiply two things the key assumption going back to chapter 10 to multiply two things is that the two things are what? What assumption did you make? So you actually just that they're independent. And that's what the test assumes as the null hypothesis, and that's what the expected counts are based. Not disjoint though, that is adding things together. To multiply two things together, we assume that they're independent, and the null hypothesis is that they're independent. So expected counts are calculated on the theory that they are independent and what we would expect. No worries. So does that make sense right here? If you look at the math, it's just probability of this times probability of this. The reason we multiply by 152 is to remove it from a decimal and turn it into a count of how many we would expect. So multiplying by 152 cancels one of the 152s, hence row total times column total over grand total can be used to calculate it. Or you could do percent of that times percent of this times grand total. That also works, but there's the cancellation. So this formula right here is this formula down here, and it's reduced. That's the more inside baseball of how it's done and why we're doing this right here to get the expected cell counts. Once again, and I'm going to bring this over here to the other screen so I can enter in all the values. We should be able to find the expecteds very easily, and for any question now that wants the expecteds, just use jump. Also know how to check it. So fatal body is 58.85. I'm totally going to make a typo. If you get, a lot of people, thank you for people watching my videos, and when I say like, please email me, please say that I said to email you me too. Like, hey Brian, you said if I missed something by a big decimal, I can get points. No, I did. I don't know. I don't say that. But I appreciate when people say, hey Brian, you emailed me that, or you said to email about this. Yes, definitely. Head and neck. Oh, really? No, it's not out of order, is it? 38.96. I'm literally copying the numbers from the numbers from the table. So copy your numbers, and 28.18. Last but not least, 5.82. It should be right. Someone can correct me when I get one of them wrong, but there's the numbers on the screen. So compute the chi-squared test statistic. This is a more laborious process. Compute the chi-squared test statistic. And let's say this for the first video, for the first question. How to get the chi-squared test statistic. Yeah, I know, right? Once you're done with this one, you're done. So how do you get the chi-squared test statistic? How do you get the chi-squared test statistic? It is sum of all cell chi-squareds. So we need to know what cell chi-squareds are. Cell chi-squareds, which is a metric of variation that each observed is away from the expected, can be found by the formula. A cell chi-squared, so it's a chi-squared of a cell, is equal to observed minus expected squared over expected. Very famous formula from Mendel and his pea plants. Nice job, Hannah. And so you'd have to do each one of these, as in write the formula for the cell chi-squared for this cell. Try to do it right now, and you can just call that 8 for all intensive purposes. Write the formula. So the observed is the count. I'll start highlighting things. The observed is the count. The expected literally is the expected. So that should show you, and you have to do it for each cell. W for pea plants right there. I'm doing genetics. Is it 6.125? It might be when you solve it. So the formula is going to be, when we write it down, observed, which is 1 minus 8. I'm just going to call it 8 for now. Over, and then we have to square that quantity, and then it's over 8. So that's 7 squared over 8. That's 49 over 8. And that is equal to, I think you're right. Yep, something like that. This is just an estimate because we didn't carry decimals. So yeah, that's a good estimate of it. So now if we carry the decimals, which jump can do for us, of course if you're taking a test, always carry decimals, we can just go right here and click the red arrow and ask for the cell chi-squareds. And the cell chi-squared is actually 6.16. Notice how we were very close, but we're not looking for the individual cell chi-squareds, which is how weird each individual cell is. We are looking for the what? So we are not, how did you know to use those numbers? Observed minus expected squared over expected. That's the formula. Which numbers are you wondering about though? You want the observed is the count. How many were in that cell? That is the ones we count. The expected is what we would expect via random chance. And then the sum of all the cell chi-squareds is just the formula we use. Good question right there. the sum of exactly the sum of which will be down here with the Pearson. So remember Pearson, because the Pearson, if you add up 0.5, 2.1, 1.3, 6.16, 5.26, 25.52, what does that add up to? If you add up every single one of those, what does that add up to? If you add up all those cell chi-squareds, mathematically you're going to get what? Like how much? Like, there we go, 40.858, the Pearson chi-squared test statistic, which is the sum of all the cell chi-squareds. I also say that when I go back here, I can look at the screen. So here's the Pearson chi-squared test statistic. Now, how many degrees of freedom does it have? What I really love about these is it's very easy to remember the degrees of freedom for this. I want you to tell me, is this a 4x2? Is it a 2x2? And do not use the totals. That's where people make mistakes. So tell me, is this a 1x1? So I'm asking like how many groups are in lethal, how many groups are in injury or site. It's a what by what. You can reverse the numbers, but tell me it's a what by what. And right there, basically, Cameron, really close. It is a 3x2. Now with holding up your hands, drop down one finger and then multiply the numbers. So the degrees of freedom, so hold up your hands here and then drop one number and multiply. Because that's rows minus 1 times columns minus 1. So now, how many degrees of freedom are there? When you multiply out, there's how many degrees of freedom? How many degrees of freedom? 2. Another classical way of doing this is to go right here and draw an L. If you draw an L across this, you'll actually delete one row and delete one column. Do not use the totals. And you can see right here, this leaves 2 cells. That's another check right there that I've come up with, is to draw the L. And then you will see that there's 2 degrees of freedom. Or you can do the classic formula, rows minus 1 times columns minus 1, 3x2, 2x1, solved. So there's 2 degrees of freedom. The degrees of freedom tell us which chi-squared distribution we are using. The p-value is basically 0. Reason being is we are so far away on this distribution. Take the L right there. Do I not have chi as one of our things? Is it exclamation chi? I thought I had chi-squared on here. Check out the chi. Good, it's exclamation chi. So with 2 degrees of freedom, that gives the shape of the chi-squared. Notice it changed shape. And we are going to find a p-value from the chi-squared, and we're at 40.85. It's 0. If we increase this, it's a very, very zero number. So it is there's basically no area to the right. You know what happens with more degrees of freedom? The chi-squared starts to become what? With more degrees of freedom, the chi-squared starts to look more and more what? Ironically, that's what happens with degrees of freedom, more normal. We won't usually see that because we don't usually go up to that high of degrees of freedom. We'll use things like computer programs to calculate it, but just like with the t, chi-squared is right skewed to start and becomes more normalized. And there is a normal approximation people use in higher level statistics. The center of it's usually the degrees of freedom, and then 2 times the degrees of freedom square root is the, I'll have to cheat. Reject or not reject the null. The p-value is 0, the alpha is 0.05. Reject or not reject the null. Reject or not reject the null. What do you think? The p-value is 0, the alpha is 0.05. Reject, and that means we have evidence, are not independent. That was a good question. Oh my gosh. I bet it's one of these. Really? You should email me. Someone say it. Let's throw out 100,000 points. We haven't thrown out points today. Someone say it. Email your instructor if you're like Brian. 2 decimals. All of those decimals. There we go. Ridiculous. Ridiculous. I was like, I don't remember entering something wrong. Email Brian, you get that wrong with the 3rd decimal right there. It should accept that. That's one of my, come on, my peers. What's up? Same sort of idea right here. It's literally the same problem. So let's do a different one because I think we've got enough time. That's literally the same problem. So let's do this one right here, which is going to be super short. This is not that long. Okay. Chapter 19 wheels. Suppose we conduct a test of independence and end up rejecting the null hypothesis. Which of the conclusions is appropriate? If we reject the null, what would we believe? Tell me in the chat. I'm not going to read the answers. If we reject the null, what would we believe? I'm not going to read the answers. I don't want you to read them either. Like when you reject the null for the chi-square test of independence, what do you believe? Why does this work and then not work? Why is it constantly changing? Yep. If you reject the null, you'd reject that they are independent. You'd have evidence they're not independent. So the two variables, we'd have evidence. I would say that. See, look at this. It's very... Well, you wouldn't believe the two variables are independent, because that's the null. The two variables are not independent, so one variable depends on the other. I might actually get this one wrong. I don't like it. Reject the null. I reject that they are independent. I have evidence they're not independent. Why do they do that? That is mean. That is mean. So one variable depends on another. Yeah, it makes it sound like cause and effect, I think. I think that's what they're going for. I would say evidence of a dependency. It's not like a bad answer. If they gave you like a wrong answer, B is just flat out wrong. A is like incomplete. And then C is what we generally say. Well, you can say there's a dependency. That's what association means, some sort of dependency between the variables. I don't like it. I was like, I think A is just 2, because I will say there's evidence of an association. Like, that's what I would say. That would be the best answer. Evidence of an association. Now, we can't say cause and effect. In dependency, they might be going towards that. I'd really like to know the person who wrote this. I think they're saying they are not... We can't say we know they're not independent. We would just say we have evidence they're not independent. We have evidence they are, have a dependency. Not the best. Let's do this one right here. I think multiple choice would be properly worded. I could have come up with a better wrong answer. Okay. Chapter 19 quiz. I remembered that one when I looked at it, and I was like, it was throwing me for a loop before. Most pregnancies go full term, but some are preterm, less than 37 weeks. Of these that are preterm, they are classified as early, less than 34 weeks, and late. There's a late preterm. Cool. A report examined these outcomes for 1 year, broke down by the age of the mother. Is there evidence that outcomes are not independent of age group? So what is the null? Once again, I want to show you this. Do not read their answers. Know how to write the null without using any help. In the chi-square test of independence, all you do is add one word between the groups. So we have age and length of pregnancy. Age and length. And what is the one word you add for the null to do the chi-square test of independence? Exactly, Cameron. Give me a full sentence, though. Go full sentence on this right here. Give me the full sentence right here. So age is X and Y is length of pregnancy. Age is independent of length. Exactly. All you do is put independent right here. And the alternative is simply going to be not independent. Does that make sense? So age is independent of length, and age is not independent of length. And think about, this is the chi-squared test of what? This is the chi-squared test of what? Which is a really good way to remember what you're doing. This is the chi-squared test of what? To see if they are this or not this. So you can remember, like, the null hypothesis for the chi-squared test of, what is it called? They can't right here. It's called the chi-squared test of, not independent, but the chi-squared test of independence. So the chi-squared test of independence has the null hypothesis that X and Y are independent of each other, and has the alternative hypothesis that X and Y are not independent of each other. So the chi-squared test of independence. Good way to memorize it right there and know what your null hypothesis is, because this one breaks the bounds of parameter equals null value. So we look for the one that kind of meets what we're looking for. Age and outcome are independent. There we go right there. It jumps right to doing the chi-squared test statistic. Good for us. So check out the earlier part of this video where I did it step by step by step. We just now need to bring this data into Jump. Slow down this video right here, because I'm going to bring it into Jump, and then we'll get the answer. Click the button, copy to clipboard. Once you copy to clipboard, click Done. Now go over to Jump and go to File, New, Data Table. File, New, Data Table. Under File, New Data Table, go to Edit, Paste with Column Names. Edit, Paste with Column Names. Make sure you have a categorical, quantitative, quantitative. If you have that, go to Table, Stack, Table, Stack, Tables, and then double-click the blue columns only. You should see a categorical, categorical, and quantitative, and click OK. Now you have your data ready to go. Notice how it's two categorical variables for the chi-square test of independence, and then the quantitative data right here. How much RAM do you have on your PC? I think 64. Yep, I got 64 gigs of RAM. So it's really good PC. Thank you, Haslam. And so now we go to Analyze, Fit Y by X. With Analyze, Fit Y by X, and 32 is good. We're going to put the, well, it doesn't matter this time. Let's go either one, because the X and Y, if you flip them, have the same relationship as Y and X. And let's put the data here in the frequency. It must look like this. If you forget to put the data down there, it won't look right. It'll be flat across. You must have the count, frequency, observations in the data. Go ahead and click OK, and it runs the full chi-squared test of independence. And we get the sum of all the cell chi-squareds down here with the 1.785. This value right here, the Pearson has your p-value, 1.785, and there's the p-value of 0.6183. We'll take a quick screenshot of that. And that's the main information we need to know. Now we go back over here into the assignment. And we take the chi-squared of 1.79, 1.785, was it? 1.785, there we go. Oh my gosh. And the p-value of, it was like, I got it. Get your conclusion. The p-value is high. Just let the null what? I don't think it's liquid cooling. Thank you for asking, Cameron. It's a really good PC. It's Alienware. It's got a 4080 in it. It's got a 4080. It might be a 3080. The p-value is high. Let the null fly. Since the p-value is high, we fail to reject the null. We let it fly. That's what we say in our class. When the p-value is high, let the null fly, just let it be, don't reject it. And so with that, we do not have enough evidence to conclude that there is a relationship between the two, i.e. they're not independent. So the p-value is greater than or equal to the level significant. There's not evidence. So I think we're just going down here to this one. The p-value is greater than or equal to level significance of this, of alpha, of 0.01. There's insufficient evidence to reject the null. Got it. And we do not have evidence to the alternative. Remember, you have to write these out. So know how to write them out, and then you'll be good. Practice it during class. So the null hypothesis for this one would be what? We have region somebody is from and they're political. So region and political view. Region is what? Do the full sentence right here, and then I'll have you do a null alternative. Region and political view. Yeah, Jacob. Give me a question. I'll do that next. We'll do that next after this one. Region is independent of political view. Exactly. And then Jacob, drop one in the chat and we'll do that. So politics. Exactly. Now we look for the one that most meets that. Political party is independent of region. That's right there. There it is. Political party is not independent of region. You can actually do things where you look for one side. That's a Fisher exact test, I believe. We're not doing that. There are ways to do tests where you find directionality in this. Compute the chi-squared, compute the p-value. So they're just jumping right into it. So this is another easy one where we don't have to do all the steps. Not really good practice. But remember, we're going to go here to copy clipboard. We're going to copy the data and copy it right here. We're going to go into Jump now and go to File, File, New Data Table. With File, New Data Table, we're going to go to Edit, Paste with Column Names. And if you want, you could call this region before you stack your table. Make sure make sure your data looks like this. It should be categorical, quantitative, quantitative. You do not want the things in the wrong sides. And it is very important that you have red, blue, blue, blue. If you mispaste it, just start over and repaste again. We're going to go to tables and go to stack. Double click the blue columns right here, and you should see the region and the party label and the data appear here. And then click OK, and you have your table ready to analyze. Now, go to Analyze, Fit Y by X. With Analyze Fit Y by X, we're going to see if region explains party label. Remember, X explains why something is happening, and the data has to go into the frequency. Once again, one of the most common errors I see is when people don't put the data into the frequency and it doesn't turn out correctly. Click OK, and you get your mosaic plot. We can see somewhat of a relationship. It looks like in the West, there are more Democrats. In the South, there is more Republicans, and independents are about equally spaced across. There's a little bit more people in the South, too, as evidenced by the total right here, 38%. And you can see the South has a slightly larger margin. The marginal display shows us the univariate amount. So make sure you know how to read a mosaic plot where you see the larger the margin is, like Democrats and Republicans are about equal. And look, Democrats have 40, that's Democrats, 44.86, so there's more. 37.38 Republicans, so the Democrats should be a little bit bigger. Notice it's actually kind of the wrong colors we use in America. You can go up here to set colors, and you can actually change it if you want to what we more traditionally think of as politics. So that makes it a little bit easier to understand if you're thinking how, wait a minute, I think it would be this, because blue Democrat, red Republican, and switch it around there. You don't need to do stuff like that. That's just if you're going to present data, which is good. Just want to make sure the final is online correct. That is correct, just like all the other tests. The chi-squared is 4.201, and the p-value is 3795. 4201. If I can do it. 4.201. I remember them? Let's see if I remember them. P-value is high, just let the null fly. If the p-value is high, then you fail to reject the null. There's not evidence for alternative. Do I remember those numbers? I did not, it looks like. So where did I make my error? I'm trying to go by memory. 3795. Wait a minute. 4 decimals p-value. It's the bottom p-value, which you can't see. 3795. 4. Really? Double check your math. There we go. So there we go. Make sure to not make errors. The first question really is the one we did much longer on. It's really the good step-by-step review. Putting things into JUMP, you need to know where you're getting them from and what they mean. What is a cell chi-squared? What is the chi-squared test statistic? What is an expected count? What is an observed? What is the degrees of freedom? What does it mean? All these questions right here. Let me write down things you should know and be able to tell me. So then we'll do the question. Well, but Jacob asked the question. Chapter 19, things you should know. Okay. So here are things you should know for chapter 19. We didn't even say all of them. What are the 4 conditions? How do we check them? Drinking glass? Yeah. How do we check them? What is an observed or count? What is an expected? What is a cell chi-square? What is the pure? Okay. Any questions on any of these right here? So these are 10 things I can think of off the top of my head that I would say you need to know pretty well for this chapter. The 4 conditions are random, 10%, expected cell counts, and count data. How do we check them? Random, make sure the data is random. 10%, make sure it's less than 10% of the total population. Count data, which I said is the 4th one, means 2 categorical variables, so political party and region you're born in are both categorical. And expected cell counts greater than 5, we look at all the expected cell counts, and each one has to be greater than 5. We can also check the smallest expected cell count. What is an observed or a count? Observed is how many we see, like in a certain area of the country. We can just look at the mosaic plot, and we observe 64. That's an observed. An expected is what is expected by random chance given the null is true, found by row total times column total over grand total. Thank you, Hannah, right there. That's what I wanted to do right here because I hope you'll use this to review. And you're getting a head start on today's lecture by being here. The cell chi-squared is a metric of deviation between the observed and the expected in that cell. We square it to make it positive. We divide by the expected to standardize it. Remember, we always do a difference, and then we standardize it with something on the bottom. And that's just a metric of deviation from that cell's expected, because observed minus expected is a difference. Square it to make it positive, so the negative sign, as Rock would say, doesn't matter. And then we sum them up to get the Pearson chi-squared test statistic as a total metric of deviation between the observed and the expected. So the Pearson is your Pearson chi-squared test statistic. That is then plotted on, well, the degrees of freedom are going to be rows minus 1 times columns minus 1. So in the previous example right here, we could look at any of them. This is a 3 by 2. Only count the groups right here, 3 groups there, 2 groups there. Reduce by 1, 2 times 1, 2 degrees of freedom right there. The degrees of freedom tell you which chi-squared you're using, because they all have different shapes to them, and I've broken the applet for the moment. And then you input, find a p-value using your chi-squared value, and then it'll plot to the right of it. It's a right-tailed test because the smallest Pearson chi-squared is 0, where all the observed and the expecteds are the same, and so the more deviation you have, the more unusual that is. That's why you can only get a chi-squared as small as 0, because you're summing up values that have all been squared. And since they're all squared, they're all going to be positive. And so the smallest chi-squared test statistic is 0. Am I lagging? I think I am. Nope. Caught up now. So weird. And the bigger the chi-squared, the smaller the p-value. As we can see, if we increase the chi-squared, we get a smaller p-value. Pretty much everything's been said about that now. It's like speedrunning the lecture. What's the null alternative? The x is independent of y, the x is not independent of y. How to write and fail to reject writing the null. I reject the null because my p-value is less than alpha. This is evidence for my alternative that they're not independent. My null was that they are independent. Make sure to give the variable names. Thank you so much, Hannah, right there. I think it is a huge help. And then I fail to reject the null that these two are not independent because my p-value is higher than the alpha. Give the values. And then I did not have evidence for the alternative that they're not independent. Let's do the drinking glass problem. I was really hoping that'd be a good review right there, and I need to change the alpha a little bit more on this. I can't wait to be 100% again. I just started working out again, and like working out while sick, and I'm not working out too hard. I'm just doing I was doing squats last night. Oh my gosh. I'm like, what happens when you like do like this like 20 times? Your body's like, what are you doing? You don't need to sit down that many times. Stop it. Your like legs and thighs start to hurt. You're like, geez, why? You sit down once and you get back up. That's all we need. I just need the ability to sit up and get but really good. It's only been 5 days. Dieting and working out for 5 days. 5 days. I'm trying to go 6 months for loading the assignment. 6 months. Can I do it? Find out 5 months and 3 weeks from now. Drinking glass problem. Just enough time. There we go. Drinking glass problem. Drinking glass, Hannah? Okay. Now, these problems, you want to know how to do them from the start, step by step. Might do a speed run, a little bit of this. But the null hypothesis, oh, thank you, William. Do that. Be like, I'm checking in, Brian. You need to write this down, William. Check out alpha stars then and be like, you do it, Brian? And hopefully I'm like, yes, I did. So the null hypothesis, so when you do chapter 17, you want to write down the null is that mu1 equals mu2. Now, sometimes we might have mu small equals mu large or something like that. And then the alternative is based on what they asked. But I think we're going to be doing something like this. Let's look at what the null and the alternative is. And we should write null before that. And we should write alternative this. And let's go ahead and take a look. The question says, do people put more liquid in one glass or another? They were given random glasses. Does the glass size change? That's the key word. Does it change how much they put in there? So the alternative is going to be that they are not equal. If you notice mathematically, it says mu1 minus mu2 not equal to 0. That's the same thing as mu1 not equal to mu2. The null would be that they're equal to or have no difference, i.e. mu1 minus mu2 equals 0, mu1 equals mu2. So they are the same as the null, and they are different as the alternative. It jumps right into finding the t-statistic. So to find the t-statistic, we need to use the formula here. So we're going to go take the math and do it. So it really boils down to knowing the formula or looking it up. The screen. And here you go. So the formula is going to be the t-statistic with degrees of freedom that are too complicated is equal to y bar, and we got to be careful because they tell us how to write the null here. They are saying it is, look, which one is mean 1? Mu1 is the population of the small glass, okay. Y bar small minus y bar large over S1 squared, or small, over n small quantity plus S2 large, S squared large, and then n large. So now we plug in the numbers right here. Get the following. The mean for the small glass is 5.11 minus the mean for the large glass is 6.91 divided by square root. And then we do 1.88 squared over 22 plus, and then you gotta be careful. I messed the math up on this many a time. It's very easy, and please call me out. I am making a math error. It happens. Reset the calculator really quick. Boop. And do the standard error first, which is the metric of variation. Standard error is a way to standardize stuff. The top part is always the difference on these tests. So 1.88, square that, divide by 22. We're going to copy that. Now we're going to reset the calculator. 2.76 squared, you can times it by itself, divided by 30. Then we're going to add the other one that we saved. So just make sure you do that properly, and then we're going to square root it. There's the standard error. We've calculated the bottom of the formula right now. With the bottom of the formula calculated, we take 5.11 minus 6.91, which is going to be 1.8, negative 1.8, excuse me, divide by the standard error, which gives us 2.79 negative. Now, what's really interesting is we can probably guess the p-value from this. Sample sizes are not too small. Round to 3 decimals, so we're going to change this to this. The p-value to 4 decimals. Oh, that's where they're being mean. That's so mean. Can I get a p-value to 4 decimals on this? 2.5758. It's two-tailed. It is two-tailed, right? And it's going to be about this. It's very, very tiny. 1.5758. It's a really hard one to guess. Really hard. State your conclusion, reject the null because the p-value is low, leading to evidence for alternative. The data provide sufficient evidence that they are different from each other. Did we get the p-value? Check answer. P-value we didn't get. It's going to be around here. And let's find out what the p-value really was. Oh, now we got close enough. Like I said, it's around there. But let's go show how to get the p-value. Okay, so we need to go to the t-applet. I was like, it's got to be around there. Okay, so here we are going to the t-applet. And so on the t-applet screen, you first need to go find the degrees of freedom for this. The degrees of freedom are going to be calculated here. And I believe we got to put in, here we go. The standard deviation for the first group is 1.88. The standard deviation for the standard deviation for standard deviation for first group, sample size for first group. Standard deviation for second group, sample size for second group. Degrees of freedom are 49.78. Now let's find the p-value, put in the degrees of freedom of 49.78, and then go to outside for the two-tailed test, drop in the values, and now round to 2 decimals. There it is. Now this is probably one of the most complicated p-values to find because you need to first find the degrees of freedom. Why did we shade outside? Because we're doing the two-tailed does not equals test. Does that make sense, Jacob, right here? This is a tougher question, and knowing the steps to complete it really shows that we understand how to do a hypothesis test. We write the, we have the HACS method, do your hypothesis, annotate the notation, check the conditions, and then solve the problem. We should be doing that more. We haven't done enough lately. Where did the 2.796 come from? That came from the negative. It's negative technically. It came from this right here. This equation right down here at the bottom. We have to solve this equation right here by plugging in the values to get the t-statistic. The t-statistic is equal to the two means subtracted from each other over the standard error. Does that make sense right there? So we have to plug in those numbers and then solve for the t-statistic. That's got it. Good work. Still up until tonight, so get it done. Good work, good practice. Let me know if you have questions. This equation right here solves for the t. T gets you the p-value. P-value tells you if you reject or fail to reject. Good to go. I'll see everyone in class. Bye for now. Good job.